In this video, we're going to take a look at models of exponential growth and decay. Let's say that the rate of change of y is proportional to itself. Let's find the general solution if y is a function of time. So let's take this a little bit by a little bit, because that can be a little bit overwhelming to look at that and say, I don't even know where to start. So first of all, we're looking at a rate of change, which of course means that it's a derivative. It's a slope. The rate of change is a slope. So the rate of change of y, and it's a function of time. So everything I have underlined in blue tells me that I'm going to take the derivative of y with respect to t, because it is a function of time. Then it says it is proportional to itself. And what that tells me is that I'm going to have some constant times the variable y. So proportional to itself, again, proportional meaning that I'm just going to be multiplying that by the constant. So the rate of change of y is proportional to itself. This is how I would set that up. Same way, if you had something where it said the rate of change is inversely proportional, then it would be k over y. So obviously inverse, meaning that you would take the reciprocal, 1 over y instead of y. But basically, here's a good starting place. Now from here, if we want to find the general solution, well, now we're going to use integration, which we've been practicing. So let's integrate, keeping in mind, of course, that we want y's with y's, and k is just some constant, so it's like a plus c type of situation, although we're not adding. But let's go ahead and rearrange before we try to integrate. So if I divide each side by y, on the left side that gives me dy over y. On the right side, I'm going to end up with k dt. And that's okay, because k isn't a variable, k is some constant. So it's okay that k and t are not the same thing. It just means that obviously that is a like a coefficient, essentially. So let's go ahead and integrate now. So we know if I integrate dy over y, that's just the natural log of the absolute value of y. On the right side, I'm going to end up with kt plus c. And again, using all of the same skills that I've been building, I'm going to end up with exponentiating each side, and that gives me the absolute value of y, which I'm going to not write the absolute value of y, I'm going to write it as plus minus, and e kt, and then of course plus c is the same as times e to the c, which means that I can write this as y equals c e to the kt. This is the general solution. So keep in mind some things that you'll want to remember about this general solution is that c is going to be the initial value of y. And that might not be clear yet, but it will be as we continue to work on these. K is some proportionality constant, which is just a constant that is being multiplied instead of added. That's why they call it a proportionality constant. Keep in mind, if k is greater than 0, that this is exponential growth. And if k is less than 0, then we're talking about exponential decay, where something is decreasing over time. So let's take a look at a practice question here. And again, this is not an application question yet. This is just so we know how to proceed when we get a question like this. So this question says the rate of change of y in an exponential growth model is proportional to y. So it's proportional to itself. The rate of change is proportional to itself. So everything that I have written in white tells me that I can use that equation y equals CEKT that I did all that work for just a moment ago. So that's all the stuff in white is telling me. Now the stuff in green says when t is 0, y equals 2, when t is 2, y equals 4. So how does this help me? Well, when y is 2, then t is 0. So that tells me that 2 is equal to c, and then e to the k times 0 is just e to the 0, which is 1. So that tells me that c is 2. And then when t is 2, y is 4. So essentially this tells me now that I have y equals 2e kt. And what I don't know is the value of k, because again, k is that proportionality constant. So essentially we're going to now solve for that. So now I'm going to do the same thing I did before. I'm going to replace y with 4. C is now 2. T is going to be 2 because I'm using this now. So k is k, t is 2. So I'm going to divide each side by 2. That gives me 2 equals e to the 2k. And then how am I going to solve that? Well, I'm going to take the natural log of 2 is equal to the natural log of e to the 2k. And remember that we can, on this side, natural log of e is essentially going to go away. So I have natural log of 2 is equal to 2k, and therefore k is equal to the natural log of 2 divided by 2. So if I use my calculator and take the natural log of 2 divided by 2, I get about 0.3466. So I still haven't answered that part in pink, but what I have done is I've been able to write the model as y is equal to 2e, and then k is 0.3466, or you can leave it as the natural log of 2 over 2, so depending on the situation if you need to be very precise, and then of course t. So here's the model. Now notice they didn't explicitly ask for the model, but you should find the model if you're then going to continue to the part in pink where it says what's the value of y when t is 3. Now before I do the part in pink, I just want to point out that again this is what that model would look like, and again when t is 0, y is 2. That's this point right here. And when t is 2, y is 4 is this point right here. And this equation, or this line, is that model I just came up with. Y equals 2e to the 0.3466t, or I could use natural log of 2 over 2 instead of my decimal equivalent. So the last part of the question asks me to find the value of y when t is 3, and again all I have to do there is solve for y by plugging in 3 for t. And again, depending on how precise they want you to be, instead of using 0.3466, I might use natural log of 2 over 2, just so that I'm not rounding in the middle of the question. But you should end up with an approximate value of 5.657. I want to take a look now at a few application questions. This first one deals with exponential decay. So suppose that we have 5 grams of the plutonium isotope that was released in the Chernobyl nuclear accident. How long would it take for those 5 grams to decay to just 1 gram if the half-life is 24,100 years? So again, we know it's decay because it says decay. Now what this tells us is that k should be less than 0, so that's a good check that you can do as we're doing our work. The other thing you should do is try to think about initial conditions. So what do they tell us? In our last question, it wasn't an application question. They just said when t is this, y was this. But now let's take a look at how we could write those for this particular situation. It says 5 grams was released. How long will it take for 5 grams to decay to 1 gram if the half-life is 24,100 years? So to me, this says we're starting with 5 grams, and that means when time is 0, we have 5 grams of the isotope, and the half-life is 24,100 years, so at time 24,100, there will be half of 5, or 2.5, left. So those could be our initial conditions, and again, k should end up being less than 0. So let's get started now. Remember, we don't have to go through all of the work to determine that this is going to be our exponential model, y equals c e to the kt. Now, we know we're starting with 5 grams. So again, I don't have to do the work because I know that c represents the initial amount. So I could plug in 0, 5 and solve, but instead I'm just going to replace c with 5. So I'm going to put a check mark next to this one because now we've used that one. And from here, of course, I'm trying to solve for k. K is what I'm trying to solve for, the proportionality constant. So I'm going to now use this information, and I want you to notice something. So if I were to plug in 2.5 for y, and for t, plug in 24,100, what I'm going to end up doing is dividing each side by 5, obviously, and I'm going to get 2.5 over 5, which is 1/2. So I have 1/2 equals e to the 24,100k. The reason I wanted to point this out is whenever we're dealing with half-life, this is always going to end up being a half. So I don't even really need this guy because I know that when I divide, I need the 2410 obviously, or 24,100, but I know that the 5 and the 2.5 are just going to end up reducing to 1/2, and it's always going to happen that way for a half-life. Okay, so from here, now we're just going to do the math, and this should be getting pretty straightforward or simple for you because we've been doing this now for a little while. So I'm going to take the natural log of each side, and the natural log of this side is going to give me 24,100k, and then that's going to give me k is equal to the natural log of 1/2 divided by 24,100. Now on this one, I'm going to choose to leave the exact value of k rather than doing any simplification. So far, here's where I am. I have y equals, c is now 5, k is now the natural log of 1/2 divided by 24,100. So that is my model. If they said write the model, I would be done right here. And again, I could reduce that k to a decimal equivalent, but I'm choosing not to do that. But now I need to actually answer the question that says, how long will it take for those 5 grams to decay to 1 gram? So again, we're trying to find for 1 gram, which means I'm replacing y with 1. So I have 1 equals 5e to the natural log of 1/2 over 24,100t. I'm going to divide each side by 5, which gives me 1/5, or 0.2, is equal to e to the natural log of 1/2 over 24,100t. I'm going to take the natural log of each side, so the natural log of 0.2. Natural log of this side obviously will get rid of the e, so I have the natural log of 1/2 over 24,100t. And then to solve for t, I'm going to take the natural log of 0.2 and divide it by the natural log of 1/2 divided by 24,100. So yes, that's kind of a lot of work. I'm going to plug all of that into my calculator. Again, I've chosen to leave this as an exact value because if I round that and then I use a rounded answer, then my final solution is less precise. So this gives me about 55,958.46709, or about 55,954 years is how long it would take for the 5 grams to decay to 1 gram. Let's take a look at another example. In this example, we're dealing with exponential growth because the number of rabbits is increasing. And also, instead of solving for t, or time, which is what we did in the last example, in this example, we're asked to find how many rabbits were there in the initial population, which hopefully when you see initial population, you think that we're trying to solve for c. So let's go look at how we could go about doing this. Again, it's a good idea to know up front that it's exponential growth. Because it's exponential growth, that means that k is greater than 0. And I forgot to check on that last one, but if you took the natural log of 1/2 and divided it by 24,100, you do get a negative value. In this case, k should be a positive value. And again, let's look at some of our initial conditions. There were 100 rabbits after day 2, which tells me that I've got 2, 100. And there were 400 rabbits after day 4, so 4, 400. So that's all I need to know. Now I can get started. And again, I'm going to be using that same exponential growth model, y equals c e to the kt. And I'm not going to know c until I get to the very, very end, but I can start solving for some other values. So let's plug in 2, 100. So 2 is t and 100 is y. So 100 equals c e to the k times 2. Again, t is 2. And what you'll find here is we have 2 unknowns. We have c, which is unknown, and we have k, which is unknown. So for now, all I'm going to do is I'm going to rewrite c in terms of k. So what that means is I'm going to divide each side by e to the 2k, which tells me that 100 over e to the 2k is equal to c. Now, you might be thinking that didn't really do anything for us, which it kind of did and it kind of didn't. What it did is it made it so I can now rewrite the equation with just one variable, and once I have just one variable, then I can solve for that one variable. So I'm going to now use this information to write y is equal to, instead of c, I'm going to write 100 over e to the 2k, and then times e to the kt. And now I'm going to use, since I already used 2, 100, I'm going to now use 4, 400. So now I'm going to say 400 for y is equal to 100 divided by e to the 2k times e to the 4k. Again, t is 4, so I'm replacing t with 4. From here, I'm obviously just going to try to do some reduction. So this side I have 400. This side I have 100. And then I'm going to do some reduction here. So if I have e to the 4k divided by e to the 2k, that ends up with 4 minus 2, or e to the 2k. Again, by subtraction, that's just a law of exponents. I'm going to divide each side by 100, so I get 4 equals e to the 2k. So now I'm getting closer to being able to solve for k. And again, that's not what I want to do. I want to solve in the end for c, but we have to find k first. So from here, I'm going to take the natural log of each side, and that's going to give me 2k, which means the natural log of 4 divided by 2 is going to be equal to k. Again, as I did in my last example, I'm going to leave this as an exact result. So from here, I can now take it to the last step, which is to write my equation. C, if you'll recall, is 100 divided by e to the 2k. Let me just back that up. C is 100 divided by e to the 2k, which means it's 100 divided by e to the 2 times natural log of 4. So it's really just e to the natural log of 4. And 100 over e to the natural log of 4 is just 4. So we have just found that c is 25. Now, are we done? Do we have to do any more? The question says, how many rabbits were there in the initial population? Which means we're trying to solve for c. I've just solved for c, so there were 25 rabbits in the initial population. Now, notice I did not write the full model, and that's okay because in this question they didn't ask me to. They just said solve for c. So that is what I did. So we can't talk about exponential growth and decay without bringing up Newton's law of cooling. And Newton's law of cooling states that an object's temperature is proportional to the difference between the object's temperature and the temperature of its surroundings. So we're going to quickly run through the general form. Obviously you can just Google Newton's law of cooling and it's going to give you the correct form, but here's where it came from. Again, it's proportional to, so just as we did before, we're looking at dy over dt, and it's proportional to the difference, so we got the k here, which is our proportionality constant, the difference between the object's temperature, which we're going to call y, obviously y is going to represent the temperature, and the temperature of its surroundings, we'll just call that capital T. So again, this part written in pink, I don't have pink available to me in my tools here, so I'm using red. All of that is rewritten as y minus t. So from here, it's just everything that we've been doing. So I'm going to get this side to be where my y's go, so this is going to be y minus t, and this side I'm going to have k dt. I'm going to integrate as I have been doing, which gives me the natural log of y minus t, and this side is kt plus c. And again, I'm going through it kind of quickly just because we've done this a lot. I'm going to exponentiate each side, so e to the power of each side. On the left-hand side, that gives me y minus t, absolute value. On the right side, it gives me e. Well, I'm going to go ahead and just do my magic c here because this is e to the c. So e to the c is going to be c, and then e to the kt. And then again, we don't have to worry about that plus or minus because c is just some constant. So from here, I'm going to rewrite this by adding t to each side, c e to the kt plus t. So it's exactly what we've done. The only difference is when we're dealing with Newton's law of cooling, we have to factor in this plus t, which is the temperature of the surroundings. Let's look at one last question together dealing with Newton's law of cooling. So we have a container of hot liquid placed in a freezer with a constant temperature of 30 degrees Fahrenheit. The initial temperature of the liquid is 130 degrees Fahrenheit. After 5 minutes, the temperature is 70 degrees. So without even looking at the part in pink, let's take a look at just modeling that question. So again, we know this is Newton's law of cooling. We have something that is cooling based on the temperature around it. So I'm going to use my model, y equals c e to the kt plus 30. Now where did 30 come from? Because the cooler has a temperature of 30. So again, this is that capital T that we said was the temperature of the surrounding. From here, I'm going to use the fact that the initial temperature of the liquid is 130 degrees. Now, when we did this before, we always just replaced C with the initial temperature, but that's not quite what's going to happen here, because if I used at time 0, so C e to the k times 0, I still have this plus 30 to contend with, so this 130 is now actually going to have 30 subtracted from it, so 100 is equal to C times e to the 0, which of course is just C. So C is 100. So that's the first part. And again, after this step, I know that my function or my model looks like this. Y equals 100e to the kt plus 30. So again, I've got a k and a t and a y that are all variables, and the variable that I really need to know the answer for is k to write the rest of my model. So that's what I'm going to do now. So I'm going to start with using, after 5 minutes the temperature is 70, so I'm going to replace y with 70. I'm going to replace t with 5 for 5 minutes. I still keep that plus 30. I'm going to subtract 30 from each side. That gives me 40 equals 100e to the 5k. I'm going to divide each side by 100, so that gives me 0.4 or 4/10, which is equals e to the 5k. I'm going to take the natural log of each side, and that gives me that 5k is equal to the natural log of 0.4, and so k is equal to the natural log of 0.4 divided by 5. Again, I'm going to keep that as an exact value instead of a rounding. So again, if I wanted to, after this step, I could say that my model is starting to come together a little bit more. E to the natural log of 0.4 divided by 5 t plus 30. And so that actually is my model. So if it said find the model, we're done. Now we have to look at the part that I have written in pink that says how much longer will it take for the liquid to cool to 50 degrees. So we're saying how much longer to get to 50. So I'm going to take this model that we've just come up with, and I'm going to replace y with 50 and solve for t. So I have 50 equals 100e to the natural log of 0.4 divided by 5t plus 30. And if I divide each side by 100, I'm going to end up with 0.5 over here. Oh, just kidding, don't do that yet. Subtract 30 from each side first, so I get 20 equals 100 e to the natural log of 0.4 divided by 5t. And now I can divide by 100, which gives me 0.2 equals e to the natural log of 0.4 divided by 5t. I'm going to take the natural log of each side. So on the left side, I have the natural log of 0.2. Oops, natural log of, wow, let me try that again. So I'm going to take the natural log of each side. And on this side, of course, that e is going to go away. That just gives me the natural log of 0.4 divided by 5t, which means to find t, I'm going to take the natural log of 0.2, and I'm going to divide it by the natural log of 0.4 divided by 5. And that's going to give me approximately 8.78. Now let's go back to our question. The question says, how much longer will it take? So it's already been the 5 minutes, so I'm going to take my 8.78 that I just calculated and subtract the 5. So it's going to take about 3.78 minutes longer. So 8.78 minutes total, but 3.78 minutes longer. That's all for exponential growth and decay. Coming up next, we're going to revisit separation of variables. So we started that in this section. We took a look at some of the simpler equations, and now we're going to get a bit more complicated using separation of variables to find general and particular solutions.